So in the last couple of videos, we've learned about work, and then we've also learned about kinetic energy and gravitational potential energy. I'm just going to remind you of the equation. So we know that work is equal to force times displacement. And then we've learned that gravitational potential energy is equal to mass times gravity times height. And kinetic energy is equal to 1/2 mass times velocity squared. And we've already derived these equations. So in this video, we're going to try to find a way to relate these three equations and then also talk about conservation of energy. So let's look at an example on the next page. Okay, let's say that I have this bookshelf and I have a book sitting 1 meter above the ground. Well, let's find the potential energy of that book, and that's a 2-kilogram book. Okay, so we already know that PE is equal to mass times gravity times height. The mass of the book is 2 kilograms. The gravity is 10. And the height is 1 meter above the ground. So I know that my potential energy is 20 joules. Okay. So now let's say that I lift this book and I place it here. So let's first look at the work that I would have to do to lift this book. Okay, so remember that work is force times displacement. So what is the force acting on the book? Aside from when I initially lift the book up, the only force I have to overcome is the force of gravity. And the force acting on the book is equal to the weight of the book. In previous videos, we've learned that weight is the same as mass times acceleration due to gravity. So the weight of this book, I'll just write the formula up here as a quick reminder. Okay, so the weight of this book is its 2-kilogram mass times acceleration due to gravity, which is 10. So the weight of that book is 20 newtons, and that's a force. So my force, in terms of the work equation, will be 20 newtons. And then my displacement is 2 meters. So notice that I'm only lifting it from here to here. So even though this is 3 meters above the ground, I'm only lifting it 2 meters, because I already started 1 meter above the ground. So the work that I just did is equal to the force, 20 newtons, times my 2 meter displacement. And that's equal to 40 joules. Okay. Now let's look at the potential energy of the book when it is on this higher shelf. So it's pretty much the same equation as this guy, but my height is different. So I'll put this in blue. So my PE, when the book is on the higher shelf, is equal to the mass of the book, which is 2 kilograms, times gravity, which is 10, times the height. And this is the height above the ground. So the height above the ground is this guy, 3 meters. And that is equal to 60 joules. So we see an important relationship here. The work that I had to do to lift the book from here to here is equal to 40 joules. That is also equal to the change in potential energy. So the final potential energy minus the initial potential energy, 60 minus 20, which is 40, gives me the work that I did to lift the book. So I'm going to put it on the next slide. Net work, 2 words, net work, is equal to change in potential energy. So that's really just equal to final potential energy minus initial potential energy. An important concept to grasp is that this equation right here is true for other types of energy as well. For example, net work is also equal to change in kinetic energy. Or Final kinetic energy minus initial kinetic energy. And the concept behind that is that energy is transferred. Energy cannot be lost or gained if there's no other external force. It's just transferred to different types of energy. So let's look at an example that's a little bit more complicated and involves potential energy, kinetic energy, and work. Okay. So let's say I have this scenario here where I've got a 10 kilogram ball that's been raised 5 meters above the ground. And I want to look at the work that was done to raise the ball, the kinetic energy, and the potential energy of the ball at various points during its free fall. Okay? So first let's consider the work done to raise the ball to this height. So we know that work is equal to force times displacement. We know that the force of the ball, when I'm just raising it up against gravity, is equal to the weight of the ball. And we know that the weight of the ball is the mass of the ball times gravity. So the weight of the ball is 100 newtons, which is also equal to the force, times displacement, which is 5 meters above the ground. So work done is 500 joules. Now let's look at the potential energy of the ball right here, right before it was released. So we know that potential energy, PE, is equal to mass times gravity times height. The mass of the ball is 10 kilograms. Gravity, acceleration due to gravity, is 10. And the height of the ball, which is the height above the ground, is 5 meters. So potential energy here is equal to 500 joules. What about if we look at the kinetic energy of the ball at this point? So kinetic energy is equal to 1/2 mv squared. So the mass of the ball is again 10 kilograms. And the velocity of the ball right before it's dropped is 0. Okay? So that means the kinetic energy at this point here is 0 joules. Okay. Now let's look at the kinetic and the potential energies right at the bottom. So right before it hits the ground. So the potential energy of the ball is equal to the mass of the ball, which is 10 kilograms, times gravity, which is 10, times the height above the ground. So again, now it's at the bottom of this cliff, so the height is 0. So potential energy, gravitational potential energy, is 0 joules. Okay. Kinetic energy. So this is a little bit harder to find, because now we need to know the velocity of the ball right when it hits the ground. We know that the mass is 10, it's just times 1/2, times velocity, we need to find velocity. So let's find velocity. We'll have to kind of draw on past lessons where we, learned about initial velocity, final velocity, acceleration, and then those 3 equations that relate them all. So in the next page, I'm going to start to set up a chart. You might remember these charts where we look at, initial velocity, final velocity, acceleration, change in distance or displacement, and time. Okay, so looking at the motion of this ball, the initial velocity here is 0. So this is 0. Acceleration due to gravity is 10. We're talking about a free fall. We don't know time. I don't know final velocity, but I do know displacement. Displacement is 5 because it went from here to here. So this is 5. Okay. You might recall from earlier videos this equation, Vf squared equals Vi squared plus 2a delta x. So I'm going to just plug in and I can find final velocity, which is what we need. So Vf squared is equal to 0 squared plus 2 times 10 times change in position, which is 5. So Vf squared is equal to, 20, 100. So Vf is equal to 10. Okay, so I know my final velocity now. Now let's find kinetic energy. So KE, plugging in, is 1/2 times the mass of the ball, which is 10, times the final velocity, which we just found on the last page, which is 10, that's squared. So I get, okay, 10 squared is 100, times 5 is 500. So we should start to see that the sum of the potential and kinetic energies at the top is 500. 500 plus 0 is 500. And at the bottom is also 500. But potential energy goes from 500 joules to 0 joules. And then kinetic energy goes from 0 joules to 500 joules. So it looks like all of the ball's potential energy was transferred to kinetic energy. And those sums equal to the work that I had to do to lift the ball above the ground. So let's look at when the ball is now, let's say, here. So halfway through its free fall, it's now at a height of 2.5 meters above the ground. So this distance is 2.5. So let's look at the potential and the kinetic energies at that point. Okay, so potential energy is probably easiest to find first. Potential energy is mass of the ball, which is 10, times gravity, which is 10, times the height above the ground, which is 2.5. And that gives me 250 joules. Kinetic energy. So again, we need to know the velocity at that point. So I'll go through the process one more time. And on the next page. Okay. So, again, setting up a chart, we know that VO is 0. We're looking for VF. Acceleration due to gravity is 10. We don't know time, and we know that the change in position is 2.5. So, plugging in, just like how we did in the last problem. Okay, so I get that VF squared is equal to, let's see, that's 2550. So VF is equal to the square root of 50. So I can plug that in over here. Remember that kinetic energy is 1/2 times the mass, which is 10, times the velocity, which is root 50, squared. Root 50 squared is 50, times 10 is 500, divided by 2 is 250. Okay, so we again see that the sum of the potential and the kinetic energies are 500. And that equals to the work that we did. It's also 500 here, and it's 500 here. So what I can do, instead of always having to find the final velocity, I can find the potential energy and then determine the kinetic energy just by subtracting 500. So I'll do that out. Let's see. So let's say I want to find the potential and kinetic energy at this point. Right here. Put it in a different color. Okay. So right here, what I could do is again, okay, so let's say this height is 1.25 meters above the ground. This is 1.25. So I know that PE is equal to the mass of the ball times gravity times the height above the ground, which is now 1.25. So I get that that's 125 joules. KE, therefore, must be 500 minus 125. And that gives me 375 joules. You could verify it by finding the velocity and, plugging into the kinetic energy formula. But this is just a faster way of doing it. So going through this whole process shows an important relationship. We see that at every single moment during the ball's free fall, its total energy, this is 500, this sums to 500, this sums to 500, and here as well, all sum to 500 joules, which is equal to the work that I put in initially. So this illustrates conservation of energy. Energy cannot be created or destroyed, it is just transferred. So the energy that I put in to move the ball 5 meters above the ground was first transferred to potential energy. Then during the free fall, some of it was potential and some of it was kinetic. And then even more was kinetic. And then at the end, potential energy was 0 because it was now at ground level, and all of the energy was transferred to kinetic energy. So this brings us to our last equation. We've already learned that net work is equal to change in potential energy, if we're just considering potential energy. We've also learned that net work is equal to change in kinetic energy. Now, when there's potential and kinetic energy, net work is equal to change in potential energy plus change in kinetic energy. Right? And sometimes you'll actually see this formula written like this. Work is equal to final potential energy minus initial potential energy plus final kinetic energy minus initial kinetic energy. You might see it rewritten as initial potential energy plus initial kinetic energy plus work is equal to final potential energy plus final kinetic energy. So this is a common way that they write that equation. Okay, so in this case, another thing to point out is that this work here can be any external force. In the last problem, it was somebody lifting a ball up above the ground. But there are other external forces. This could be like force of friction or an external push, anything. You just have to take into account any additional external work done. So this sort of wraps up our video on conservation of energy. In the next video, we're just going to talk about specifically in the case of springs, and then move forward.